So, where are we at here? So I'll scroll down. So hopefully you saw my announcement. I kind of extended the due date on that problem set a little bit. I wasn't going to get to grading it, so I figured if you still wanted a couple of days, I gave you them. So I said kind of keeping an eye on Canvas announcements. That's how I'll communicate to you outside of class. So I think I had it set to be due at the end of the day yesterday. So I'll just take your most recent submission. If you did, submit it and then rework it, submit it again, I'll just use the most recent submission. I should start getting those graded here this week. We should be good to go with classes this week. 99% sure I won't be here on Tuesday. So I'll probably have a video recording posted after Thursday's class. I should have it ready to go by then already. Actually, depending on what we get through this week, I've already got it ready to go. But we'll kind of have replacement video for next Tuesday's class. There might be a replacement video for next Thursday's class as well. Once again, keep an eye on Canvas announcements. That's how I'll kind of communicate to you about that. But we should be good to go for this week. I put up the next problem set yesterday. So that problem set and quiz have kind of passed. Where are they at? They're up here. I put up the next set of sample questions. So the next quiz, I'll likely post it after today's class, although I would probably hold off on taking it until after Thursday's class because we're still going to cover some material that might be on the last question of that quiz. So you've got your practice problems. You can start looking at those to get an idea about what the quiz is going to look like. You've got that 5th problem set. That'll be really what we did with interaction terms, and then a little bit of what we talk about this week. Okay, so you can really get started in that already, even after today's and Thursday's class. And I kind of have that set tentatively to be due at the end of next week. Okay, I may be generous with the quiz and extend the due date on that a little bit to be kind of over Thanksgiving. Over that problem set, I want it to be due next Friday so that I can kind of try to get that graded over Thanksgiving break. Once we come back, we should just have one more problem set and one more quiz, and then we'll kind of have a couple more weeks of class. So review week, and then we'll have the final. Okay, so that's kind of where we're going. This week, we're talking about kind of different issues that can exist with our data. I've got the slides up there, as well as a do file. I might open another do file today, which I'll probably put up after class. It's nothing that I'm going to expect you to do, though. So if you want to use it as a reference, you shouldn't need it for like the problem set, but it's just kind of showing you the power of what we can do in Stata. Okay. Any questions for me before we kind of get going here? Good. All right. So there we go. We'll start. So we're going to talk about 2 different types of what we call validity and how different issues in our data can threaten us. Now, we've already kind of talked about one of these. It's just we haven't been as explicit in it. So we have internal and external validity. So internal validity is just going to be that whatever causal effect we're trying to estimate with our regression, it's not going to be reliable, or it's going to have some bias. So what are some things we've already talked about that can cause bias in our estimates? If we have an important, so if there's something that's not in the regression that should be, we have an important omitted variable, right? What did we talk about before interaction terms? Nonlinearities. So maybe we have the wrong functional form, right? We talked about even with nonlinear or with interaction terms, maybe there's a relationship between 2 variables that makes the marginal effect of one of those variables that varies with the other. So those are all threats to our internal validity. Our external validity threat are going to be a little bit more broad and kind of harder issues to resolve, I would say. So external validity, I guess the general idea would be like, let's say I'm interested in the effect between, I don't know, the hours studied for a test and performance on that test. Well, if the data I have comes from college students, should I be using that data and applying it to, I don't know, middle school students on some standardized test score? Probably not, right? They're 2 different groups. So sometimes when we have our regression results, the group that we use from our data set is not going to be, we can't extend it. It doesn't have external validity to all other groups. Now, ideally, what we try to do in economics is come up with these basic, like underlying principles that extend across multiple different areas so that for example, if I can understand, I think we looked a little bit like, I introduced this idea of like the hot hand effect or like gambler's fallacy. That can be applied to a lot of different topics. If I can use any data, could be sports gambling data, could be, could just be looking at, performance on a stupid like little game, like where I'm throwing a ball in a bucket or something like that. If I can understand the basic mechanics, I can apply it to a lot of different types of data sets that would have more external validity. Okay. So we're going to be concerned about both of these, or you can think about external validities. How can we generalize our results? Okay. So I already kind of used this example. So some real threats to external validity are going to be differences in populations. This was kind of like the example I used, that results from college students might not apply to high school or middle school, right? Or maybe I have the results from the United States, right? Maybe I want to know the relationship between income and savings. Well, maybe that looks very different in the United States than it does in Moldova, right? I have two very different populations there. Difference in settings can matter. So even if we have the same subject, so let's think about my college example. If I were to look at the effects of ad campaigns on alcohol consumption, my guess is it's going to be very different at IU than it is at BYU, right? You don't know BYU is, I just heard the other day, I didn't know this. If you're part of the Church of Latter-day Saints, you automatically get half price tuition there. So, I mean, very different populations. So here I've got the same college student population, but it's very different settings. Okay? So these are all things, these are kind of examples of threats to external validity. So just to give you a very basic example of what this looks like with data, I'm going to have that data issues do file, and we're going to be using this life expectancy data. So let me open that up here. And I'm actually going to copy and paste this up here so I can have it to use, so that I'm not using my own computer. I should have set a global, but I'm just going to use this life expectancy data, right? So I've got this open. I'm going to run a regression. So I've got BMI and GDP, right? How does GDP impact BMI? And I chose a log model here, just, I don't know, to make the interpretation nice and easy, right? GDP are really large values. So if I were to run just a regular regression of BMI or GDP, and rehash some of these ideas we talked about, what's going to be true about the size of my coefficient? So if I were to just simply run a regression of BMI and GDP, what's the size of my coefficient going to be on GDP? So how would I interpret that coefficient? If GDP is measured in US dollars, if I've just got a linear model, it's a one what change in GDP? Which would be $1. So is the effect going to be really large or really small? Probably really small, right? So if I run this regression, just kind of make this point, excuse me. Yeah, e to the negative 13, move that decimal 13. This is an insanely small coefficient, right? So just to make it a little bit easier, I said, and I'm not sure if it's the correct model. We've talked already about how I would determine that. But here, I'm just going to use the log model, so our interpretations are a little bit easier, right? So I'm going to run one of these where I'm only using developed countries. So there was this variable in the data set that identified it as it was a developed or a developing country. So here I've got two very different groups. Notice, if I estimate the relationship between GDP and BMI for developed countries, well, there, as a country has higher and higher GDP, well, I'm not controlling for a lot of omitted variables here, but what would this suggest? A 1% increase in GDP does what to BMI? I'm okay with awkward silences. If GDP goes up by 1%, what's going to happen to BMI? Goes down by 0.002%. So still a pretty small effect, right? But there is some relationship, and it looks like it's statistically significant. P-value is basically 0. Now, that was for developed countries. So if they have more and more money, maybe they become more focused on their health. We actually see their BMIs lower. In developing countries, well, food is still scarce. So there, a 1% increase in GDP, what is that doing to my BMIs? It's actually increasing them by 0.0015%. Now, it's not quite statistically significant, right, on the other side of 0.1, but pretty close, right? So this is kind of an example where you can see, depending on the group I'm running this regression for, my coefficient estimate might be wildly different, right? So what's one way I could maybe solve this? So we have this external validity threat. I think that the relationship between GDP and BMI might vary. What's something we talked about I could do? So if I think the effect of GDP varies across whether or not it's a developing or developed country, I could include so I can include a dummy variable to control for that. Remember, we're estimating the effect of GDP and we're saying it looks different.
Okay. Could you regress them against each other?
So what I could do is something like this, right? So I've got that natural log of GDP. Should treat it as continuous here. I could interact it with whether or not that was a developed country, right? So one kind of solution to external validity, if I think there's concerns that the effect might vary across these populations, I can include an interaction term with that continuous variable. I think the marginal effect might be different for developed and developing countries and interact it, right? Now I can estimate the relationship that there might be a different marginal effect from GDP for developed versus non-developed countries. Okay. But this is just kind of an example. I could also do the same thing with GDP and population, just to kind of prove, or not prove, just to run through another example. Well, here, the relationship between GDP and population, it looks a lot more similar between these two groups, right? So in the sense of, if I'm estimating the relationship between GDP and population, maybe that result can be a little more generalized. Right? As I have more individuals, my GDP generally increases by about the same amount, right? These coefficient estimates, they are a little different, right? They're a lot closer than my other two. Okay? So some results we have will fail external validity, some of them won't. Any questions on that idea before we keep moving? It's not too tough. I think that's an easier one we'll talk about today. So, excuse me. Let's focus a little bit more now on internal validity, okay? So in order for us to have internal validity, this was that it's not about taking our result and applying it to another population. This is, did we obtain the correct coefficient estimate? Is it what we call consistent and unbiased, right? So consistency referred to whether or not we're getting the correct statistical significance. Unbiased referred to, are we getting the correct value for the size of that causal effect? So what are some things that we talked about, right, that might threaten this? Kind of already mentioned them at the top of class, but omitted variables, functional form misspecification. In terms of consistency or our standard errors, what's maybe we haven't talked about it for a while, but something we talked about that can impact that, heteroscedasticity in our error term. Right? So all of these things were threats to internal validity, and we're going to try to come up with ways that we can solve it, right? So we already talked about one, just to review it, because we're going to use it and apply it into a slightly different context. If I have an important omitted variable bias, so I can run the regression even if I don't have data on that omitted variable, right? I could then think about, okay, what are the likely variables that I don't have data on? I should. And then we could think about, if I were to include those in my regression, but what bias might exist, right? Because I'm not. Right? And so we talked about ways we can like sign that bias. So one thing we're going to introduce, it's a little bit different. Let me see if I have it here. I don't. So, if I have the data, it's very easy, right? If I think a variable matters and I have data on it, what do? I put it in my regression and see if it has statistical significance. Now, if I don't, right, there we said we can sign the bias, right? So we'll use this in a little bit. So I'm just going to write it out so we have it ready to go when we get there. But we said the estimate we see, right, is going to be the actual effect. Thank you. Does that look a little better?
Yeah.
Okay. But it will also include the effect of the omitted variable times the covariance of whatever variable we included and that omitted variable divided by the variance of the variable included, right? So we talked about things here. We're like, okay, well, what if I think that this is a positive effect, but that I have some bias that's also positive. Well, there I know I'm going to see an estimate that is a little too high. So generally, we want to err on the side of caution. If we think that there's an effect from something, we know that this bias would cause us to see an estimate that's too large or overstate the effect. What if my bias was negative? Well, then the coefficient that I'm seeing is going to be a little bit closer to what value? So if I have a positive effect, but I've got this negative bias, when I leave that important omitted variable out, my estimate is going to be getting closer to 0, right? So sometimes, and we can't completely say that with an omitted variable, because if it was a large enough negative value, it flips the sign. We talked about examples where that can happen. But as long as we just think it's going to make it closer to 0, well, there we're just understating the effect. We would call that attenuation bias. So we like attenuation bias more because there we're understating effects. If we have the opposite, where the bias is positive, and that's pushing us further from 0, well, now we might be overstating. So erring on the side of caution, we prefer to have an attenuation bias. We prefer to have no bias, right? But if we have to have one, we want it to be attenuation bias, something that's pushing that effect that we're going to see closer to 0. Okay. So hopefully this looks familiar, right? We've used this before. Yeah.
Okay, so just a real quick question. When you're using logarithmic models,
Mhm.
you're asked to apply, it's like the better fit. Then you can look at the R-squared value, but if you're comparing two logs, let's say, or maybe a linear and a log,
Mhm.
can you say that the log is better because it's more elastic? Like the log model is better for certain situations because it's it accounts for more elasticity.
Not, so if you're comparing,
You're comparing log linear.
or sorry, I'm doing X's. Log linear to log. So let's say I had this and I had this. There's two things. I can't compare results if the dependent variable is ever different, right? Because then I have different variation in my Y variable. If I have something like this, I can compare my R squareds or my adjusted R squared. They should both tell me the same story. I can also look at the statistical significance on both of these coefficients. Whichever one is more statistically significant, that would suggest that's the preferred model.
Right. I'm trying to find it, but it was a question on the homework set. And you couldn't use that because the p-values were very, very similar. It was price versus.
Oh, yeah. So there, I think I wasn't trying to trick you. But if you can't look at the p-values, what tells you the p-values?
Yeah, what's it called?
Our test statistic.
Yeah.
So you can compare the test statistic, and there you'd be looking for, well, what makes the p-value smaller? Whichever one has the larger test statistic. And there, I think in that question, you can tell which one has a larger test statistic.
I'll find it on.
Okay. So hopefully, like I said, hopefully this bias with the omitted variable looks familiar. Okay. So we already kind of talked. What if I don't have? Well, I can sign the bias, right? So what are some solutions we can use? So we won't talk about these yet. This is going to be actually what we go over after Thanksgiving break. So we're going to be talking, well, actually next week we'll start panel data, but panel data, we have some solutions that we can resolve this omitted variable bias, even if we don't have the data. We also can use something called instrumental variables. And then I have a link that I will try to get posted to class. I don't know if it'll be relevant this semester, but the economics department has a lot of these economics experiments where they're always looking for subjects, right? So one way that we can control for factors is in a lab, right? We can, in fact, they'll do things like have you act like a firm and set different prices and quantities. But at the same time, they're making sure demand is always the same. In the real world, when we have data, we can look at price and quantity data, but there's all these other factors that are changing supply and demand, and it's hard to get data on them and control for them. In a lab, we can. So another way that we can kind of resolve this internal validity threat of omitted variable bias is in experiments. Now, we won't talk about those in this class, but that, just to be complete in our discussion, that would be one thing. Right? So to your kind of point earlier, we also have this functional form that threatens internal validity. We've talked through those issues, how we determine which model might be a better fit. Now, what we didn't dive into, and I don't know if we'll have time this semester, but if you were to take, I think it's 470 or 471, the next econometrics course, you would dive into what are called probit and logic regressions. So we said, what's one problem if I want to look at functional form? What variables can I not use as my dependent variables? So if I'm taking the natural log, what variables could I not use? So we can't take the natural log of what value?
Was it 1 and 0?
Yeah, I can take the natural log of 1, but if I have a dummy variable, I can't take the natural log of 0. So these dummy variables, we couldn't kind of look at different functional forms because we can't take the natural log. We have a different way of doing that, which are probit and logic regressions, which would be kind of the next level. So we won't probably dive into this in this semester, but on top of the stuff that we've talked about, that would be the next step. So I'm going to kind of mention some things that we might not do in this class, but kind of show you where you'd be going if you kind of continue to take econometrics. So the one that we will really focus on today is going to be this internal threat, not omitted variable bias. What kind of is? It's like a form of omitted variable bias, which is going to be measurement error. So when we look at actual data, right? Let's say I had survey data. Well, it doesn't have to be survey data. Well, I'll use survey data and then I'll give you another example. Let's say I go out and I'm collecting data and I ask people to self-report their drug use. What do you think is true about the data I have? If I asked all of you what your drug use is, what are all, yeah, it's going to be vastly underreported, right? So when I rely on these data sets where I can see self-reported drug use or even self-reported income, those values aren't going to be completely accurate. Now, if I go and get income data from the IRS, I'm not worried about measurement error there, right? But a lot of the times when we have these data sets, we're going to have some measurement error. I'll give you another example where it doesn't have to be just like this survey data. So survey data is the easiest one because we know people lie, right? And we know that people will lie in certain directions, underreport, overreport. What if instead I had like medical data and I had blood pressure readings from actual doctor's visits? Why would I still have measurement error there?
People are nervous to go to the doctor.
People are nervous, or yeah.
People that are going to the doctor because they have higher.
So you're actually thinking about something we call selection bias, which we'll dive in. I don't know if we'll do today, but we'll Thursday for sure. But it could even just simply be a blood pressure cuff has a certain measurement error on the tool itself, right? It's not going to be a completely accurate reading. So we're going to have measurement error that exists not just in like self-reported data, but any data that we see. Well, not any data, but a lot of other data that we see. So we're going to make this differentiation between X, which is the actual value, which should be, if I could precisely measure it, and then X tilde is the value we actually see in our data set. So if I'm thinking about my drug use example, X would be the actual person's drug use, X tilde was the value they reported, okay? So our measurement error, we're now going to have, it's not the same as the error from our regression, but we're thinking about the error that exists in the data. It's whatever the actual X value is minus what value we see, or I think I have here, what value we see minus the actual X value. Okay? Doesn't matter which way we really write it. I think I wrote it this way because it makes it a little bit easier once we plug it into our linear regression equation. So if I'm running a regression with the actual data, okay, well, the true effect should be beta 1 times X. Okay? But the actual values I'm seeing in the data are X tilde. Right? That's the one that includes the measurement error. So notice I can kind of rewrite this. This would cancel. The true effect really should be beta 1 times the actual X values. Okay. So I then kind of, oh, that's not what I want. Hold on. I want this to be, this should have been X. There we go. That makes a little more sense. There we go. So here's the actual effect from X. But if the values that I see have this error, and I also have the error built in. So what's going to cancel here? Beta 1 times X. And I'm simply left with beta 1 times this X tilde. So when I run this regression, I'm running the regression with the variable that has measurement error in it. So I can kind of think about this, right? I've got this new U term. It's going to include not only, oh, actually, no, I had this right. Sometimes I look at things and I second guess myself. There we go. Whoops. That's what I wanted. I'm rewriting this here. I'm going to run the regression with the values I see in my data set X tilde. I'm rewriting my error term to have the usual error. So remember, our usual error from regression was the difference between the actual Y's and the predicted Y's. But I'm now going to have this additional component in my error term, which is the effect that's coming from the measurement error that exists in the data. So my U is now going to have the kind of typical error that we would have, plus some error that exists from our measurement error. So you can kind of think about that as our what we call our composite error term, right? Anytime we have measurement error, it's going to be whatever the usual error term would be, plus this additional component, right? So what's one condition that we had that needed to be met for our regression results to not be biased? We said we need the expected value of our error term, right, across these different values for X to be equal to 0. Well, now it's not the actual X values. The regression we're running is the one with the like self-reported, right? The values we see in the data. So will this still hold? Will our composite error for different values of that we see in our data set, right, X tilde, will that expected value of the error still be equal to 0, right? If it's not, then our assumption is violated, right? So if this is true, our assumption is violated, our results are going to be biased. So I'm going to go through this proof. I'm not going to make you guys reproduce this, but kind of give you an idea about where it comes from. So I'm going to rewrite. So if I had the actual X values, so like this is like if I had actual drug use data. Well, I can rewrite X as the self-reported X value minus this error term. And I'm just kind of rearranging what that measurement error equation was. Now, if I kind of rewrite this component, I now have the coefficient of the self-reported drug use data minus that coefficient times the measurement error. So if I'm now thinking about my composite error term, it's going to have kind of two components in it. So if I'm running this regression with the self-reported drug use data, my coefficient is going to be biased. Why? Well, it's almost like I have an important omitted variable. Right? So if I think about the estimate I see on X tilde, it's going to include the true effect of what that X variable has, plus this additional bias that's created because why? Well, I kind of have like this important omitted variable, right? So what's that bias going to be, right? Well, I've got the covariance between the X value I see in the data set and between this composite error, right? Negative beta 1 times the measurement error plus our traditional error. And then divided by the variance of X. So this should look, like I said, kind of similar to our omitted variable bias. It's just the omitted variable is really our measurement error. So we can rewrite this, right? I can just say, well, what is X tilde? X tilde is going to be the actual X values plus my error term. Now, if I think about why did I kind of get rid of, and I just rewrote X tilde down here as well as X plus the error term. So that's all I did right there. Now this component, why did I get rid of that epsilon? Well, because I know the covariance of my error term, even with this self-reported X value, that's going to be 0. That was our traditional error that came from our regression. We were always assuming that that difference between our actual and predicted Y's, that covariance of that error term with our X values is just 0. So that kind of goes away. However, when we move from this to that, all I'm doing there is just rewriting things, right? The covariance of X with, there you go. Covariance of X with our measurement error, as long as our measurement error does not depend on the actual values of X. So I'll give you an example where this will apply and not apply. let's say self-reported drug use data probably doesn't meet this condition. Because who's probably, if I had really high values for drug use, I might vastly underreport. So the measurement error will be really large. But for really low levels, maybe on low levels of drug use, I might be less likely to underreport it. So there, the measurement error would depend on the value of X. Now, what might not depend on that, here's an example where let's say I was trying to estimate the relationship between, I don't know, the amount that's invested in savings and income. Well, if I have self-reported income, nobody knows, well, not nobody. People don't remember exactly what they're not going to give you the correct amount in the sense of like, yeah, I'm going to make 54,000. Well, their actual pay stub was 54,928. And I make about 60,000. Well, their actual pay stub was 58,700. So there is going to be measurement error, but regardless of the amount of income you have, you're not going to report, you're just getting close, right? So there, the size of the measurement error doesn't depend on the income level of the individual. So the covariance of the actual income of the error would be zero. There's no relationship. Now with self-reported drug use data, that's probably not the case, right? Because there, when drug use levels are high, it's likely you're going to have a much larger measurement error, right? They're going to underreport by larger amounts than people who aren't having a very high level of drug use or alcohol use, whatever you want to use, or whatever you want, example. So if we do have this hold, excuse me, that's what we'll call classical measurement error. The measurement error does not depend on the actual values of that X variable. So if that's the case, well, now the covariance of the actual X values in our error term, that's just zero. So all we're left with is the covariance between our error term and our error term. Well, that's just the variance of the error measurement error term. So I can rewrite this as, right, negative beta 1 times the covariance of the measurement error with itself is its variance. And then here, I can rewrite the variance of X plus the variance of the measurement error like this, because it should be rewritten with like a covariance between the two, but we already said the covariance is zero. So all of this, right, if we have classical measurement error, we're going to end up with this equation down here, which is the actual estimate we're going to see. Well, it contains the true effect, beta 1, plus this additional component. So our estimate is going to be bias, right? So I can then take that bias. I'm going to just rearrange things a little. I've got the same constant in both of these, so I'm going to pull that out front. I'm going to rewrite the variances how we typically would write variances. And then I can rewrite this as the variance of X over the variance of X plus the variance of the measurement error. So this is just math, right? So notice here, when I have classical measurement error, the estimate that I see will be the true effect, but is it always going to be what? So that estimate I see will always be less than or greater than the actual effect. But what has to be true about that fraction?
Positive.
Yeah, as long as the measurement error has a variance, anything other than zero, it's not only positive, but what's true about this fraction? It would be, if I take something, divide it by itself plus another positive value, this fraction will always be. So if I take 100 and I divide it by 100, what value do I get? 1. If I take 100 and divide it by 100 plus any amount above 0, my fraction will be less than 1. So we know that when we have classical measurement error, the estimate we see from our regression is going to capture the true effect multiplied by something less than 1. So it's always going to be closer to 0. Or we have this, what I mentioned earlier, attenuation bias, right? So because we have that classical measurement error, we kind of work through the mathematics, we end up with this is our bias, but that fraction has to be less than 1. We always know that with classical measurement error, our estimates are always going to be a little bit too small, right? A little bit closer to 0. Okay. And once again, one way we can solve this. We'll eventually, the last topic we cover in this class is instrumental variables, and then more advanced techniques. Okay. Any questions over that before we keep moving. Excuse me. So that was classical measurement error. If I go back, when I have non-classical measurement error, this covariance between the actual X values and our measurement error was not equal to 0. So we actually had this additional component there. Then we don't end up with attenuation bias. We can actually end up with bias in any direction. It can be too high, right? We can actually see it flip signs. We'll do some examples of this. So like a good example of this is self-reported, right? The drug use one is pretty good. But if I have like self-reported intelligence, what we tend to see, people who are really smart, do you think so for high levels of intelligence, when they self-report their intelligence compared to those who have very low, people who have very high intelligence might think that they're, well, I know all the things I don't know now. So all of you probably don't think you're that, like, all you like, I don't know this stuff. I'm not that smart. You're at a D1, a Big Ten university, right? You've made it this far, like you are already well above the average, right? So your intelligence, you will probably underreport your intelligence by quite a bit. Now, where I live, I kind of live out in the country, and I've got a neighbor, and it's kind of your classical, there's about, 10 things that probably don't run in their yard. There's things from the 70s still that he thinks he knows everything, right? So for individuals who have lower level intelligence, you don't even know what you don't know, right? You might think because you have a good mastery of algebra that puts you well above the majority of the population. So their self-reported intelligence of someone with lower might actually be that they over-report. Well, now the measurement error is directly related to the values of X, the values of intelligence. That would be something that would be non-classical measurement error. And now our results, we can't just say they're going to be closer to 0. We don't know what's going to happen, right? But we could, but for the sake of this class, we're not going to dive in. We just know they're going to be wrong. They're going to be biased, okay? So I think I have, an empty slide here because we're going to dive into these issues. Yeah, I don't think we'll get to the dependent variable today based off of, well, we go to 11, So let's go to this do file. And I'm going to reopen this life expectancy data set. I'm going to change the GDP variable just to make the coefficients a little bit easier to look at. I'm just going to scale it because GDP is like in trillions. So I'm going to scale my GDP. I'm then going to run my basic regression. Okay, if I had the actual, I'm going to go through like thought experiments here to prove to you what I'm saying about measurement. So here's the original actual GDP data and BMI, right? It's kind of an example, but here we are, right? So I've got the coefficient, the true effect of a 1 unit increase in BMI on predicted GDPs is that it should increase GDP by about 60, and then what? 1, 2, 3, 1, 2, 3. So I did million, 60 million, no. Yeah. No, 600, so it'll be 60,000 times a million. So yeah, 60 trillion, no, $6 trillion, right? A large effect, right? We're just focused on the value here, okay? So if I'm going to set this seed so that if you were to like run this, we're all going to have the same random numbers, right? I'll kind of show you how we can get around this later on, but just so we have the same numbers for right now. So I'm then going to create this new variable that I'm going to call measurement error, right? So this measurement error, I'm just going to say it's somewhere between 1 and -1. So I don't know why it exists, but there's some measurement error that exists in my data. I'm then going to create this new BMI variable. So here, I've only been talking about measurement error and X up to this point. So measurement error in our independent variable, right, that right-hand side variable. So my new variable of BMI measurement error, it includes the true BMI value plus some measurement error. So this is like, for whatever reason, if I didn't have the actual data, and this is all I had, right? So I can actually kind of create this measurement error to kind of prove what's going to happen if we had it. So if I now run this regression where I've got GDP, but I'm not using the actual BMI values, I'm using the variable that has the measurement error built into it. What should happen to my estimate? We just said, if we have classical measurement error, so here, my measurement error was completely random. From a uniform distribution, it didn't depend on the values of BMI at all. So what should happen to my coefficient? We said that fraction, the variance of BMI divided by the variance of BMI plus the variance of the measurement error. That fraction should be less than 1. So my coefficient should be smaller.
Smaller than so.
So sure enough, if I run this, I get something less than 60,000. Okay. In fact, I could go through, I could summarize BMI, figure out what the variance is, plug that in. I know the variance on my uniform distribution here. I could plug that in. I could figure out what that by should be. I actually will kind of work through that. If not today, we'll look at that on Thursday.
So it generates the errors.
Yeah. So in practice, before we get to this, you don't want to do this, right? You don't want to create measurement error, but I'm creating it to show you, like, what if you did have self-reported data that included the measurement error? Yeah. But what this is doing is it's creating that measurement error that's classical, just completely random. And then I'm kind of creating this like hypothetical variable, which was like I went out and collected the data and it had the measurement error baked into it.
So how does it differ from like your standard error values? I know obviously it's between 1 and negative. It's not a number greater than 1, but when you're running that command.
This command?
Yeah, what is that?
It's just generating random numbers somewhere in between. So, no, I can show you. It's a good question. So there's somewhere between 1 and -1.
But it's not associated with anything like action.
Nope, completely random. Right. So I'm just assuming, like, let's say I went out, I'm doing this thought experiment. Like if I had the actual BMI values and then I had self-reported BMI. I don't have both of those in my data set. I'm kind of artificially creating, like, what if I did have a variable that had that measurement error? Then it was completely random, right? So I'm baking in that measurement error completely random. Okay. So in like practice, you can't really do this with actual data because usually all you have is just the variable that has measurement error in it. And you don't know what that measurement error, where it comes from. Or like you don't know if it follows uniform or normal, but I'll show you, it doesn't really matter in the long run. Okay, so are we with me at least up to the point, the fact that we have this attenuation bias? So what should happen if instead I'm going to create this measurement error, and instead of being from -1 to 1, it's going to have a wider range. So if I have this uniform distribution, but it's a wider range of values, what's going to be true about the variance of my measurement error? So instead of being between 1 and -1, it's between -10 and +10, my variance is going to be larger, right? I have more variation in my measurement error. So what should be true? Well, we said, whenever we have this classical measurement error, the coefficient estimate we see, and here we're looking at BMI, will be the true effect of BMI on GDP times the variance of our X variable, which was BMI, over the variance of our X variable plus the variance of our measurement error. So if the variance of our measurement error is increasing, what's going to happen to our fraction? So if the denominator is larger, our fraction is going to go down. These aren't like hard-hitting questions, right? So if this fraction is lower, what's going to be true about the estimate I see? Well, if I'm multiplying something by a smaller value, the estimate I see is also going to be even closer to 0. Okay. So I've got this second measurement error that's much larger, right? So if that was instead the measurement error that existed, I'm going to create this new BMI that includes this large measurement error and then run a regression with that. So what should be true, not only do I see an estimate that's lower than 60,000 now, I should see something that's lower than 53,000, right? The value I found when I had small measurement error. So I'm going to go ahead and run this. Sure enough, I'm all the way down at 7,000 now. When I've got this really large measurement error, it's quickly pushing my coefficient down to 0. Now, notice, what is that also going to do? So even if standard errors stay the same, although they will change, notice what happened with the statistical significance when I had small measurement error. Okay, well, it's not the right value, right? It's not 60,000, but it's still statistically significant. So if I ran this regression and I didn't know the measurement error existed, I'd still be rejecting the no, I think there's a relationship between BMI and GDP. But if I had really large measurement error that existed, not only was the coefficient a lot smaller, remember, how do you calculate a test statistic? Well, for a coefficient, it's just you take that coefficient estimate and you divide it by standard error. So if my coefficient estimate is falling, it's likely that I'm also going to have a smaller test statistic. So notice what ends up when I have really large measurement error. Now it starts to lose statistical significance. It's still statistically significant here, but not at the same levels. It's only statistically significant now at that 10% level, not the 1 in 5. So not only will this attenuation bias cause us to have a bias in our estimate, it's also going to start to influence our statistical significance. Any questions on this idea before we keep moving here? Let me see what examples I have here. Yeah, we might do this before we get out of here. So the next thing I wanted to show you. So we've got classical measurement error. We worry about it because it's going to influence the coefficient size that we see. Now, would I be as worried? So let's say the variance of BMI, I don't know, let's say this doesn't make sense for BMI, but let's say we had some variable and the variance was 1,000. And the variance on my measurement error was 2. Am I going to be as concerned about that measurement error? No, right? Because that fraction is going to be really close to what? 1. Right? So the amount of measurement error we have also matters. If we think that there's going to be a wide range of measurement error relative to the variable we're looking at, well, that's going to influence our coefficients a lot more. What if I had instead, need another color. Say this was 2, right? If the variance is 2 and my measurement error is 2, well, what is this fraction now? 1/2. So now I'm only going to be getting half the size of the coefficient, right? It's going to be a much larger impact on that estimate that I see. So I care about the measurement error a lot more when its size relative to the variance that exists in the variable is much larger, right? So sometimes you can get an idea about this. Let's say in my data set, I only have reported drug use, but in some other data set, they have self-reported and aggregate. Well, there I can kind of get an idea about what the measurement error is. And if it's relatively large relative to that variance of drug use, then I might be concerned that I'm getting a really strong attenuation bias there. Okay. Is that clear what I'm saying there? We're okay with this? Getting a lot of people looking down and not at me, so I'm just making sure. Okay. All right. So all of that breaks down. We said if we have non-classical measurement error. If the size of the measurement error depends on the actual values for X, all bets are off, right? So I'll give you an example of this. Let's say I had a measurement error that I created, and it's going to be this random measurement error, but it's also going to include, and this is like the most egregious form of like non-classical, but let's say part of that measurement error is 0.1 times the actual BMI values, right? So they're the size of my measurement error. There's some randomness to it, but it's also going to be dependent on the actual values of my X variable BMI. So if I create this measurement error, and I then create BMI that includes that, now when I run my regression with non-classical measurement error, I get a smaller coefficient, and it looks like attenuation bias, but it may not be. It depends on what that actual covariance is going to be between measurement error and BMI. So I've got a second one where I can kind of show you, well, what if instead our measurement error had a slightly different relationship with BMI? We had the random component, but we also had now it's not plus 0.1 times BMI, but it's minus 0.2. So it still has a covariance between our X variable and our measurement error. But now if I run this regression, oh, I didn't run it yet. There it is. Now I get an estimate that's actually higher. Right? Our old estimate, our original was 60,000. Now I get 64,000. So depending on what that covariance is, whether or not it's positive or negative, I can see estimates that are too high or too low if I have non-classical measurement error. Right? And then you could kind of like do even wilder ones, right? So here, this is like just a different relationship. Now I'm getting 37,000. So here, like how much lower or higher that coefficient is, it's going to be dependent on what the covariance is between that measurement error and the actual X values, and we often don't know what that is. I know what it is here because I was like creating it, but in practice, if we have non-classical measurement error, we can't say what's going to happen to that coefficient. It could be higher, it could be lower, it could be a lot lower, it could be not as, not too far from the true effect.
If you ask a question like that, what would just not be asked a question?
So it's more of a broad, so I'm kind of showing you this data. What I want you to know is if you have non-classical measurement error, this is the idea that the measurement error depends on the values of your X variable. If that's the case, we don't know what the bias is going to be. All we know is that a bias will exist.
There's no way to find it.
Not based on what we've talked about. Yep. And in fact, in practice, it's really usually not a way to find it either. Classical measurement error we can, right? Like I said, even if you don't have it in your data set, you can go out and figure out what the variance of the measurement error likely is from another data set, and then kind of sign your attenuation bias. So for example, you can work in both directions. This is a good question. Let's say I found, going back to the classical measurement error, 54,000 approximately. So I knew, just kind of rewriting this, that I had some measurement error. In fact, I think we can do this. Actually, sometimes I shoot myself in the foot by doing things on the fly, but I think we can do this one on the fly. So this was, and I'll be a little more, so this is about 53,968. So this was when we had the small measurement error, right? And in fact, I'm going to go back. Well, should have a variance. No, it won't. So let me see. Let's do normal. I'm going to cheat here a little bit. So instead of a uniformly distributed variable, I'm going to use a measurement error that came from a normal distribution, right? Just so we can make this point. So let's instead, because I think this is valuable and we do have enough time. So let's go back before I do this because it's a good question. So let's reopen that data set, recreate this variable, set the seeds so we're getting the same random numbers. Now instead, I'm going to not grab measurement error values from a uniform distribution, but I'm going to grab them from a normal distribution, right? So they're still random. It's just coming from different. And the reason why I use this is because if I have a normal distribution, mean 0, variance or standard deviation of 1. So I'm now going to run this regression. And now instead of 60,000, I see 54,107, right? It's a little bit lower. It's because I was using a different function to generate these random numbers. So let's use that value. So I've got 54,107 is the value that I saw using the variable that had measurement error in it. Now I can kind of cheat because I also had the actual BMI values and I got a coefficient of 60,088. Well, if I have the actual BMI in my data set, how can I find the variance? I mean, hopefully this isn't too bad. How would I find the variance? Sum, BMI, use that kind of detail option. Okay, well, the standard deviation is 2.19, or no, sorry, yeah, 2.19. So what would my variance be? 2.19 squared or 4.81. Right? So 4.81. What's the variance on my measurement error? Well, because I did this as a normal distribution, I set the standard deviation to be equal to 1. Well, standard deviation squared, 1 squared is 1. I knew that my measurement error had a variance of 1. So if I, for example, let's say that I run my regression and I know that I have measurement error in my BMI. And maybe I even know what the measurement error is because this wasn't self-reported BMI. Maybe this was just because the machine itself has a certain measurement. Like a lot of medical companies or a lot of companies know this. Like when we go out and we record these things, we know there's a certain error, right? We're going to be within a certain range, but every device isn't 100% precise every time. So we might know what the measurement error on our device is. We have the values that the device recorded, and then there, maybe I go out and I say, okay, can I find, a pretty accurate data set of BMI and figure out what the variance looks like in BMI for this specific country or whatever I'm looking at? Well, if I have the variance on the X variable, I have the variance on my measurement error, even if I can't see this, what could I do? Well, I've got everything plugged in here. There's just one unknown. It's one equation. So what can I do? Well, I can figure out what this fraction is. So if anybody wants to help me, I'll try to use Excel to cheat here real quick. Well, not cheat, do the math for me. But so if I took what? 4.81, divided that by 4.81 plus 1, I get approximately, so this would be what? 54,107 would be equal to, well, I don't know the true effect. I only know the effect that I got from that data that had measurement error in it. This fraction I just said was what? 0.827883, right? How can I solve for this? Just divide both sides by what that fraction was. If I do that, so what? Whoops, this is falling down on me. Trying to do too much. 54,107 divided by that 0.82. So I'm getting 65,000 here. So where is this coming from? I truly should be keeping these out to like more decimals, right? But this procedure you could use to kind of back out what that coefficient would be. Now, if I ask you some of the problems that are quiz, I truncate those decimals so that we're not as concerned about kind of rounding errors, right? Where this kind of comes from is that 4.81 is rounding pretty egregiously in terms of how many decimals I should be keeping it out to. Same kind of thing with the 54,000. But this thought process is how you like back out what this coefficient is. Okay. All right. So, any questions? Any other questions? I kind of went off script there a little bit. Okay. So we talked about non-classical measurement error. This is for next class. I do want to kind of show you something here, which is, let me make sure this is the one I want. Yeah. So, in all reality as well, when I'm running this regression, my random numbers, in order to do this thought experiment, I truly shouldn't just be using one set. I should be doing this like 1,000 different times and then figuring out kind of what the average coefficient across those 1,000 different times was, right? So let's say I want to open this data set just to kind of show you what you can do. And this will be kind of a little bit more, I don't know if cool is the right word, but it'll be more informative next class. I can actually create functions in Stata. So this is nothing I'm going to expect you to do on a problem set. This is more of me showing what you can do in the kind of next step. Now, it's also, I'm going to use it to make some points about the things that we're talking about, so it's not completely irrelevant to like your problem sets or quizzes. But I'm doing the same exact thing we just did. I'm scaling that GDP variable. I'm generating this measurement error that's completely random, so we have classical measurement error now. I'm then going to create this BMI, which was the BMI plus this random measurement error. I'm then going to run that regression, and every time I run this regression, right? So I've got my program defined. So this isn't going to do anything. when I run this line of code, nothing comes out of it. It's essentially creating a function that now I can use moving forward. And whenever I use the name of that function, I call it myRed, it's going to do all those steps for me. So this next thing I'm going to do is I'm going to simulate, right? There's a simulate command. Basically, you can run that regression over and over and over and over and over again and store the results from every single regression. So what this simulate command will do is it's going to go through my program and do that 100 times. So it's going to create 100 different sets of random variables. Notice here, I wasn't using that set seed command because that set seed made sure I was getting like, so the way that random numbers work in like a data management program, or really any coding, like there is some, it's not completely random in the sense that it needs a point to start out at. So it's always going to have like the same kind of starting. So you will get random numbers, but it's going to be the same random numbers if you set the starting point to be the same. Now, what these programs will do is they always are choosing a random starting point and then generating random numbers. So that way you're not always seeing the same random numbers. But if you set the seed to be the same starting point, you would always get the same random numbers. Don't worry about that, right? That's going a little more into the coding than I want you guys to know, but that's what's happening. So here, I haven't set the seed. So I'm going to get a bunch of different sets of random numbers. I'm then going to save my coefficients and my standard errors from that, okay? So I have this program defined. I'm now going to simulate or run that program 100 different times. Oh, what didn't it like? Oh, excuse me. It didn't like that I'm not doing this from my computer. I'm doing this from here. So I need to make sure that my program has the right file path, right? So this is where globals become very important, which I should have been using technically, but there we go. So now what we see is, okay, when I was going through this whole thought experiment before, and I was using that 54,000 in order to kind of prove this to ourselves, the actual value I should have been using, well, this was from one set of random numbers. If I were to generate 100 different random numbers, I'm going to get like the average of all of those is going to be what that coefficient should be, right? So if I go back here, the actual coefficient, the average across these 100 different random numbers, 100 different sets of random numbers, was actually 50,210. So if I go back to my Excel file that I was doing here, and I use instead 50,210, notice I get something a lot closer to that 60,688. So what I really need to do is not just use one random set of random numbers. I need to do like 100 or 1,000 and figure out what the average coefficient estimate would be. Now I can back out that exact coefficient. So here is just kind of one example of using like a built-in program. You could do, I think I've got it here, like basically what we were doing. I wrote out for you. I just kind of have it in this code. So I will post this code up there for you. All right, you could take 60,088, multiply it by the variance. So that was the variance we talked about earlier in BMI. Here we had a random, normal distribution, so just one. And you could back out what that coefficient is. And what you'll find, it's exactly equal to that, well, with rounding, very, very close to that 50,210. Now, what if I run this same thought experiment, but I now create a new function where I'm doing the exact same thing, but notice, now I'm not generating random numbers from a normal distribution 0 to 1. And this is, remember, the mean and then kind of the variance or the standard deviation. So here, if I now have a mean 0, but the variance or the standard deviation, I forgot to change this, right? Standard deviation here is now 10. Well, if I've got a much larger measurement error, what should happen to the coefficient estimate that I see? So if I have a larger variance in my measurement error, what's going to be true about the coefficient that I see? Well, if the denominator is larger, my fraction is smaller, I should be seeing a lower value. Anytime there's more variation in that measurement error, the estimate we see should be lower. So instead of that 50,000, if I now run 100 different regressions with 100 different sets of random numbers, but coming from a normal distribution that has a wider distribution or a larger variance, the mean of those 100 should be something smaller, closer to 0. So I'm going to go ahead, define this program where it's going through all these steps. Once again, I need to make sure though, and someone's rocking out, that I'm using the right file path, right? So I'm going to define this function that's going to go through, create the random measurement error, but with a larger variance, run the regression, save the coefficient estimates. So I'm going to have that program in the, use the simulate, use my new program that has the larger variance. Sure enough, notice now the coefficient estimates I'm getting with that much larger variance down at 3,000, right? Quite a bit smaller. Okay. Any questions over kind of what I did there? Any questions of what that would look like? So I could do a similar thing there. So let's say, why did I know that would actually be the value? Well, because I had the actual data, so I kind of knew what the true effect should be. Well, now here, the variance of the measurement error isn't 10, I believe, or sorry, isn't 1. I believe that when I set this, I think this is actually the standard deviation. So the variance would be what? 100. So now, if I try to do this in Excel, just to kind of prove this to ourselves, I've got what? 60,088 multiplied by 2.19 squared divided by 2.19 squared plus 100. Did I put too many? Yeah. All right. I get about 2,700, pretty close to that 3,200. Really, to get really precise, I shouldn't be running this simulation 100 times. I should be running it something like 1,000 times, right? But that's, you can kind of see there, larger measurement variance to measurement error, much more attenuation bias. We're getting a lot closer to 0. So we're not as concerned with measurement error when it's relatively small, right? Where there's not a lot of variation in it. But when there is, there might be concern. All right. Any questions on anything there before we kind of call it here for today? So what we'll do next class is talk about measurement error in the dependent variable. We then also have a few more issues. Someone jumped the gun or picked up on it earlier with selection issues. We'll then also talk about missing data issues. And all of these will kind of go through all the fair game for that quiz or on that problem set. Like I said, even after today, you should be able to get through most of the questions on that problem set. I think only the last one was referencing measurement error. The quiz has a couple more, those practice problems have a few more stuff that comes from this week. So I'll post the quiz, but I would hold off on taking it until after Thursday's class. Okay. Other than that, questions for me before we're going to get out of here today. Okay. So I know we're getting kind of nitty gritty here. This isn't my favorite week, to be completely honest. The next topics we'll go through, I think, is a little bit more interesting because we can see, all right, we've got these issues, but how do we actually solve it? How do we actually deal with it? So we'll come up with tools for that. So keep an eye on Canvas announcements. Like I said, expect next week we'll likely not have class in person, especially on Tuesday, possibly Thursday. But keep an eye on Canvas for announcements related to that. Other than that, I'll see you guys on Thursday. Okay?
That's just a